First created by Isaac Newton in the 17th century, the mathematical concept known as calculus has allowed humanity to understand the world in ways never once imagined. Differentiation, integrals, and cross-sectional area, all fundamental tools used by mathematicians, but there is one aspect of calculus that even you and I can use: optimization. Building, say, a deck, is something many of us find ourselves doing, but how do you buy the right amount of materials? Imagine you're building a deck against the back of a house. Given a fixed amount of fencing, how do you build the largest possible deck? Let's say we have 100 feet of fencing. We'll call the width of the deck x and the length y. Since only 3 sides need fencing, the constraint becomes 2x plus y equals 100. Now we want to maximize the area of the deck. Area is a equals x times y. But we need a function with only one variable, so we solve the constraint for y. Y equals 100 minus 2x. Substitute that into the area equation. A of x equals x times 100 minus 2x. Expanding that gives us a of x equals 100x minus 2x squared. Now comes the calculus. To find the maximum area, we take the derivative. A prime of x equals 100 minus 4x. Then we set the derivative equal to 0. 100 minus 4x equals 0. We then get x equals 25. That means the optimal width is 25 feet. Plugging that back into the constant gives y equals 50. So the largest possible deck happens when the dimensions are 25 by 50 feet. As you can now see, optimization can be quite useful in building a man-made area. But what if you're dealing with a set area? What if you had to find a different value? A fence. Suppose a farmer needs exactly 5,000 square feet of land for livestock. The question is no longer how to maximize area. The area is fixed. Instead, the goal is to use the least amount of fencing possible. This becomes a minimization problem. Let the rectangle have dimensions x and y. The area constant is x times y equals 5,000. The perimeter, the amount of fencing required, is p equals 2x plus 2y. We solve the constraint for one variable. Y equals 5,000 divided by x. Then we substitute that into the perimeter equation. P of x equals 2x plus 10,000 times x to the negative first. Now we can differentiate. P prime of x equals 2 minus 10,000 times x to the negative second power. We can then set the derivative equal to 0. 0 equals 2 minus 10,000 divided by x squared. Solving this gives us x equals the square root of 5,000, which is roughly 70.71. And because x times y equals 5,000, y is also approximately 70.71. The rectangle with the smallest perimeter is actually a square, so you would need 283 feet of fencing. Optimization can also be used in business ventures. When dealing with profits, you would have to formulate your revenue function and subtract your costs to find the true total. Imagine an arcade selling ticket bundles for games and prizes. Suppose the arcade discovers that when ticket prices increase, sales decrease in a predictable way. Let x represent the number of $1 price increases. The arcade's revenue function might look like this. R of x equals 10 plus x times 500 minus 20x. The first part represents the new ticket price, while the second represents the number of customers still buying tickets. The arcade also has expenses: electricity for machines, employee wages, repairs, and prize costs. Suppose the cost function is c of x equals 2,000 plus 30x. Profit, as always, p of x equals r of x minus c of x. Substituting everything in gives p of x equals 10 plus x times 500 minus 20x minus 2,000 plus 30x. Expanding and simplifying gets us p of x equals negative 20 times x squared plus 270x plus 3,000. Now we can use calculus to find the maximum profit. When we take the derivative, we get p prime of x equals negative 40x plus 270. We can set the derivative equal to 0. 0 equals negative 40x plus 270. That gives us x equals 6.75. That means the arcade should raise ticket prices by about $6.75 above the original price to maximize profit. To optimize is to wonder, to envision a better world. Whether it's building something with what you have, building around your ideas, or doing something the best you possibly can, calculus can change the world.